in chapter 7 we have two modules. In module 1 we have parallel vector fields and a very important curvature called Gaussian curvature of the surface. Parallel vector field resembles with the geodesic which was done in the previous chapter. So, let us start with parallel vector field in the first section, and afterwards in the second section we shall find the Gaussian curvature of the surface. So, let us consider a surface is immersed in Euclidean space E3 and a curve C on S is given by the equation u alpha equals to u alpha S. So, the equation is represented by the parameter S, that is the arc length, and coefficient of first fundamental form is A alpha beta. If A alpha is a surface vector defined along C, then the intrinsic derivative of A alpha along C is given by del A alpha del S equals to A alpha comma gamma du gamma ds, where alpha and gamma are the surface indexes and it is running from 1 and 2. Now, this expression will come to dA alpha ds plus A beta alpha beta gamma du gamma ds. This is coming from the covariant differentiation of the vector A alpha. Now, let us consider del A alpha del S equal to 0. That means, intrinsic derivative of A alpha with respect to S is equal to 0. That means, dA alpha ds plus A beta gamma alpha beta gamma du gamma ds equal to 0. Now, if A alpha is taken as unit vector tangent to some point, then A alpha can be written as du alpha ds, and that we have expressed earlier as lambda alpha. So, now if we replace A alpha by lambda alpha, then the expression 1 will reduces to d2 u alpha ds 2 plus gamma alpha beta gamma du beta ds du gamma ds equal to 0. Which can be expressed in the form du alpha ds comma beta du beta ds equal to 0. So, again this equation is represented in the form of covariant differentiation. So, we can state the following theorem, that the vector obtained by the parallel propagation of the tangent vector to a geodesic always remains tangent to geodesic, because del A alpha del S equal to 0 gives us the parallel vector field. That means, the tangent vector is parallelly propagated along the geodesic. Now, we introduce a new curvature of surface which is known as Gaussian curvature or the total curvature of the surface. On a surface, we have first fundamental form d square equal to a alpha beta du alpha du beta. The Riemannian curvature tensor is given by with this expression. Earlier we have obtained the Riemann curvature tensor for a space which is written in the form of R H I J K, because I J K H these are the space index, alpha beta gamma delta are the surface indices. So, here we are expressing this Riemann curvature tensor for a surface and it takes the form this one, R alpha beta gamma delta equals to del u gamma gamma alpha delta minus del u delta gamma alpha beta gamma plus gamma rho beta delta gamma alpha delta gamma minus gamma rho beta gamma gamma alpha gamma delta, where this gamma alpha beta delta etc. are the Christoffel symbols of second kind. Now, from this R alpha beta gamma delta, which is a tensor of type 1 3, we can get the associated tensor of type 0 4 by the inner product with A rho alpha. So, A rho alpha R alpha beta gamma delta is equal to R dash rho beta gamma delta. So, it is a 0 4 tensor and rho beta gamma delta all are varying from 1 and 2. Now, by properties of Riemann curvature tensor, we have R dash alpha alpha gamma delta equals to 0 equals to R dash alpha beta gamma gamma, because if the first two indices are equal, the Riemann curvature tensor vanishes. So, these relations come. The only non-vanishing components of the Riemannian tensors are R dash 1 2 1 2 or its negative. So, only these two Riemann curvature tensors will not equal to 0, others will be equal to 0. So, Gauss has defined curvature of surface by, it is denoted by capital K, that is equal to R dash 1 2 1 2 by A, where A is the determinant of A alpha beta, which should not be equal to 0. So, this relation number 2 is the definition of the Gaussian curvature. It is also named total curvature of a surface. In general, the above expression can be written as r dash alpha beta gamma delta equals to k epsilon alpha beta epsilon gamma delta. So, it is in permutation tensors we can express this r dash alpha beta gamma delta in the following way, where epsilon alpha beta is equal to root a e alpha beta and epsilon upper alpha beta equals to 1 by root a e upper alpha beta, where e alpha beta and e upper alpha beta are the E system which was defined earlier, and epsilon alpha beta are the permutation tensors. Now, if we take the inner product with epsilon alpha beta epsilon gamma delta in both sides, we are getting that epsilon alpha beta epsilon gamma delta r dash alpha beta gamma delta equals to k, because if we just calculate this index in the right hand side, we are getting this 4 k. Therefore, we have k equals to 1/4 of epsilon alpha beta epsilon gamma delta r dash alpha beta gamma delta. Now, from the above equation we can say that k is an invariant. Now, multiplying both sides again by a alpha delta, that is the contravariant part, a alpha delta a beta gamma, we get this relation. Now, the left hand side is coming to a beta gamma r beta gamma, and in the right hand side we are getting, by applying the definition of epsilon alpha beta, k a e alpha beta e gamma delta a alpha delta a beta gamma. Now, again in the left hand side, by the operation of a beta gamma r beta gamma, it is coming to r, which is the scalar curvature of the surface, and in the right hand side we are getting minus 2 k by a, that is equals to minus 2 k. So, this is a very important relation between the Gaussian curvature of the surface and the scalar curvature of the surface. That means, the Gaussian curvature is equal to minus r by 2, where r is the scalar curvature of the surface. Now, let us see about the orthogonal curvilinear coordinate system. And for orthogonal curvilinear coordinate system, the Gaussian curvature is coming to this form, minus 1 by 2 root a del del u1 1 by root a del a22 by del u1 plus del del u2 1 by root a del a11 del u2. Now, how this one is coming? Because for orthogonal curvilinear coordinate system, we have a12 equals to 0. Now, using the formula r dash 1 2 1 2, if we take the inner product with the contravariant part of the fundamental metric tensor for surface with the Riemann curvature tensor of 1 3, we can get the value of the Gaussian curvature K as this one. Now, which is a very essential formula to find the Gaussian curvature for orthogonal curvilinear coordinate system. With the help of this formula, we can easily find the Gaussian curvature of a surface if their curvilinear coordinate system is orthogonal. Now, let us see how we can calculate this Gaussian curvature. For a sphere of radius r with parametric equation x1 equal to r cos u cos v, x2 equal to r cos u sin v, x3 equal to r sin v, we are going to find the Gaussian curvature. Now, we know the definition of A alpha beta from the previous chapter. It is the product of two partial derivatives. So, calculating A12, we get that it is coming to 0. As A12 is equal to 0, that means the curvilinear coordinate system is orthogonal. So, we can apply the previous formula to obtain the Gaussian curvature. Now, we find the A11. The value of A11, if we calculate by this expression, we are getting this is equal to r square. A22 is coming to r square cos square u. And the value of A, which is the determinant of Aij, that means it is a 2 cross 2 determinant A11, A12, A21, A22, the value is coming r to the power 4 cos square u, and this is not equal to 0 obviously. So, if we put the values in the formula of that k, we are getting this form. Now, if we just calculate the partial derivatives and putting the values, we are getting this one, and after simplifying we get the value of k equals to 1 by r square. That means the Gaussian curvature is equal to 1 by r square, where r is the radius of the sphere. So, in this way we can calculate the Gaussian curvature if the coordinate system is orthogonal. But if the coordinate system is not orthogonal, then we can find the Gaussian curvature by its definition, that is r dash 1 2 1 2 by A. So, you have to calculate the r dash 1 2 1 2, and from that expression we can find the value of Gaussian curvature. So, in the previous two sections of chapter 7 module 1, we have learned about the parallel vector fields on a surface and a very important curvature named Gaussian curvature of a surface. We have seen the relation between the Gaussian curvature and the scalar curvature of a surface, and we have also obtained the formula to find the Gaussian curvature if the curvilinear coordinate system is orthogonal. Now, in section 3, we shall study a new type of surface is called developable surface. It is very interesting to see here that how Gaussian curvature can be used to determine whether the surface is developable or not. So, in section 3 of module 1 of chapter 7, we shall learn about developable surface. Now, before coming to the developable surface, let us see the isometry between two surfaces. What is the isometry between the two surfaces? Consider the two surfaces given by S1 equal to y1 equal to u1 cos u2, y2 equals to e1 sin u2, y3 equals to a cos hyperbolic inverse u2 by a, which is also a surface of revolution. This surface is a surface of revolution, and its dsn square, the first fundamental form, if we calculate, you can easily calculate this one, you get this expression u1 square by u1 square minus a square du1 square plus u1 square du2 square. Now, if we consider another surface, that is y1 equal to v1 cos v2, y2 equals to v1 sin v2 and y3 equals to a v2, which is a helicoid. So, ds2 square, that is the first fundamental form for helicoid, can be calculated as this one dv1 square plus a square plus v1 square dv2 square. Now, if we consider v1 equals to square root of u1 square minus a square and v2 equals to u2, then the two surfaces have the same metric. So, we can say that if two surfaces S1 and S2 be such that there exists a coordinate system with respect to which the line element on S1 and S2 are characterized by the same metric, then they are said to be isometric. So, we can say that surface of revolution and the helicoid are isometric surfaces. The transformation of the parameters is called isometry. Now, we come to the definition of developable surface. A surface which is isometric to the Euclidean plane E2 is called a developable surface or simply a developable. So, when a surface is isometric to the Euclidean plane E2, it is called a developable surface. For example, a cylinder, cone are the developable surfaces, because for cylinder we can easily transform it into Euclidean plane E2. For cone also we can transform it into Euclidean plane E2 by giving some suitable transformation. But torus is not a developable surface. Now, for E2 we have r dash 1 to 1 2 equal to 0, as it is a flat surface. the Riemann curvature tensor of type 04 is equal to 0, and therefore, the Gaussian curvature is also equal to 0. The surface with Gaussian curvature 0 are isometric with E2, and so they are developable surface. So, this is an important idea that if we obtain that Gaussian curvature is coming to 0, then the surface will be a developable surface. So, we can assert that if k equal to 0 for any surface, then it is developable. Now, let us check whether this given surface is developable or not. Y1 is given as a function of U1, Y2 is also a function of U1, and Y3 is equal to U2. This is an arbitrary surface. So, we are checking that whether it is developable or not. Now, from the definition of A alpha beta, it is del xi del u alpha del xi del u beta, where alpha beta is running from 1 to and I is running from 1 to 3. We can find that A12 is equal to 0. If we calculate this one, we find that A12 equal to 0. That means, the curvilinear coordinate system is orthogonal. If we find A11, this is coming to this expression. And if we find A22, it is coming equal to 1. So, if we calculate the value of A, that is the determinant of A alpha beta, we are getting this expression, where f dash denote the derivative of the function with respect to u1. Now, as A12 equal to 0, that means the curvilinear coordinate system is orthogonal, we apply the formula for Gaussian curvature, and putting the values, we calculate this one, and after calculating we get this one equals to 0. So, for this surface the Gaussian curvature is 0, that means the surface is developable. So, for finding whether the surface is developable or not, we have to find the Gaussian curvature. If it becomes 0, then the surface is developable, otherwise it is not. In module 1 of chapter 7, we have learned 3 things. In the first section, we have learned about the parallel vector fields on a surface. In section 2, we have learned the definition of Gaussian curvature and how it is related to scalar curvature. And in section 3, we have defined the concept of isometry between two surfaces and the definition of developable surface. We have seen that under what condition a surface will be developable surface, and for a surface to be developable, the Gaussian curvature should vanish. So, with this we end the module 1 of chapter 7.